So now we're going to discuss a solution people often don't think about, which is a mixture of a gas in a liquid. And the idea is a fairly simple one, which is that the amount of gas which dissolves in the liquid depends on the pressure of the gas above the liquid. So if I just draw a little beaker here that has some liquid in it, and I imagine that I have some gas, which I'm going to draw as a few little molecules above the solution, there will be a few molecules dissolved down in that solution. So why is that? The reason is that, of course, these gas molecules are flying around and bouncing off the walls of the container, but occasionally they run into the solution. And while they're different than the liquid, that is, if I have nitrogen molecules floating around and this is water, it's not that they're turning into liquid nitrogen, but there is an interaction between the nitrogen molecules and the water molecules, which allows them to dissolve. So let's think about this more quantitatively and look at the definition of Henry's law. So Henry's law simply states that the amount of gas we have in the solution depends on the pressure of the gas above the solution. So let's imagine we're looking at nitrogen, which is dissolving into water, and the partial pressure of nitrogen in this particular container is, say, 0.5 atmospheres. And the partial pressure in another container is 1 atmosphere. So if we visualize those molecules floating around, here maybe we'll just show that there are 6 molecules in the gas phase, but here we have twice as many molecules in the gas phase. If here we have some concentration dissolved, the concentration that's dissolved at the higher pressure will be twice as many. That is, the number of molecules which are dissolved is proportional to the pressure. Greater partial pressure and we have more dissolved. A couple of key ideas to also imagine is we can think about the concentration. The concentration of the molecules in the gas phase is fairly low. They're spread far apart. But generally, the concentration in the solution is even lower. 10 times, usually 100 times lower than it is in the gas phase. So we only get a little bit of gas dissolved. Can we quantify that amount? We can. We quantify this using Henry's law. And Henry's law states that the amount of gas that's dissolved, which we can look at as the mole fraction of the gas, is proportional to the partial pressure of that gas. And proportional means that it's equal to a constant times that pressure. So that is, the mole fraction of the gas is equal to some constant times the partial pressure of the gas. And this constant depends on both what the solvent is and what the gas is, what the solute is. Because it depends on the intermolecular forces between solute and solvent. So if I was looking at nitrogen dissolving into water, there would be a Henry's law constant for nitrogen gas in water. Now, this mole fraction is just a measure of the amount of gas, and so again, that's the moles of gas divided by the total moles of solution. So if I was looking at N2, it would be the moles of N2 divided by the moles of N2 plus the moles of water. One of the real unfortunate things about Henry's law is that no one can decide on which equation to use. They all have the same idea. The amount of gas is proportional to the pressure, but the way they write the law is very different. And we can see that if we just look at this table I stole from Wikipedia. Here we have 3 different versions of Henry's law, 4 different versions of Henry's law, none of which is the version I just gave. They're all the same. They relate the pressure and the concentration to a constant. But this first one, it's the pressure divided by the concentration is a constant. This one, it's the concentration divided by the pressure is a constant. This is the pressure divided by the mole fraction is a constant. On the previous page, I had the mole fraction divided by the pressure was a constant. And here, I have something where I have 2 concentrations divided by each other as a constant. It's important to realize how to distinguish between these two, and the way to figure it out is always the units. The units tell us the relationship between the pressure and the concentration, and in particular what concentration unit we're using. So when you get a Henry's law constant, remember, it depends on the solute, which gas is it, the solvent, in this case this table shows the constants for water, and the units, which tell you about what concentration and what pressure are being used. So one other key idea about the solubility of gases has to do with the change in the enthalpy upon making a solution. So for gases going into a solvent, delta H solution is less than 0. That is, this process is exothermic, and typically we think of forming a solution as being endothermic. This has an important consequence for gases, which is that their solubility, that is the amount of gas that we can get into a solution, the solubility will go down as the temperature is increased. And usually we think of solubility increasing with temperature because most things are endothermic, but the solubility of gases is exothermic, and therefore the solubility goes down as the temperature goes down. Cold water will dissolve more gases than warm water. And you can see this very easily with a pot of water on your stove. As you start to heat it up, the first thing you notice is small amounts of gas coming out of solution, and that's because the solubility is decreasing. So let's summarize these ideas. The first and most important one is that the concentration of the gas in the solution is proportional to the pressure of the gas over the solution. The next important idea is that that proportionality constant, which we give the symbol K, and sometimes as a KH for Henry's law, this depends on both the solute, what is the gas, and the solvent, because it has to do with the intermolecular forces between those two. And finally, we have the idea that the solubility of gases goes down as the temperature goes up. And those are the key ideas about solutions of gases dissolved in liquids, which we quantify using Henry's law.